Welcome back. So this is going to be the next lecture of Gerhard Knieper on coarse hyperbolicity and other stuff. So please.
Okay, so welcome again to my last lecture, and you see the title of the last lecture. It's about the uniqueness of the measure of maximal entropy, and the setting which I introduced right from the beginning. So my setting is the following. So you have a closed Riemannian manifold without conjugate points. So as I said, this manifold can be represented as the universal covering, which is diffeomorphic to Rn modulo a discrete subgroup. And to get meaningful, dynamical or interesting results, we put two hyperbolicity conditions to this manifold. The one, H1, simply means that there exists a second reference metric of negative curvature, and H2 is the divergence properties of geodesics in the universal cover, which start from a common point, so they diverge. So this is an assumption which might be not necessary because one doesn't know whether it's always true, and but the first assumption is certainly somehow something like that you need. Maybe there's some other hyperbolicity condition, but that's a very convenient one. And under this assumption, so if you are really proved already that under this assumption there is a nice invariant measure which is induced by the Petersen-Sullivan measure and which gives rise to a measure of maximal entropy. But the question is this measure characterized by the fact that the entropy is maximal? And so it's important now to look a bit closer on certain invariant sets. And one invariant set I introduced already last time, it's the expensive set. And what does that mean? The expensive set consists of unit tangent vectors in the manifold, which have the property that if you lift the geodesics, the corresponding geodesic, to the universal covering, that this geodesic will connect the points at infinity in a unique way. So there's like a negative curvature, you would want to have that this particular geodesic connects 2 points in a unique way, and that in terms of Horo spheres, it means that it's not completely transversal, but it's at least a topological, they are topologically somehow transversal. So that's a picture. So what the expensive set is, and of course then you have the complement, the non-expensive set. And I already mentioned last time there is a problem if you want to prove uniqueness, because potentially you could have two measures of maximal entropies, one sitting on the expensive set and the other one is sitting at the non-expensive set. And to rule out this possibility, there comes a third condition, which we called entropy gap assumption, namely, so you are looking at somehow the topological entropy of the non-expensive set, which can be defined in the following way. You take the supremum over all metric entropies of measures which have their support in the non-expensive set. So all probability measures which have full support on the non-expensive set. And to rule out this possibility that you have two measures of maximal entropy, we assume that you have a gap in the sense that this should be strictly smaller than the topological entropy. So that's a assumption, and that is my third condition actually. So in the following, I always assume that this condition holds. So you have this entropy gap condition. That's now the third condition, and it's denoted now by H3. So H3 is the third condition. And I already mentioned that in my old work from 89, I was covering manifolds of non-positive curvature, which have some hyperbolicity, so the rank 1 manifolds of non-positive curvature. And I proved without even thinking about entropy gaps that the measure of maximal entropy is unique. And from that, I could deduce that the entropy gap holds. So that's what I got as a consequence. Here, the opposite way around. We assume the entropy gap, and then we want to prove something. Okay, so now the question is, when is this entropy gap fulfilled? And it's very easy to see, relatively easy to see, that for surfaces, there's no problem. So if you have any closed surface of genus bigger than 2 without conjugate points, then of course I mentioned already that of course you have a metric of negative curvature. It's given by the uniformization theorem, and the other thing is divergence of geodesics. That's also fulfilled, but also the third condition is fulfilled, namely the topological entropy of the non-expansive set is 0. And this is relatively easy to prove. So let's assume that your measure is ergodic and that it has full support on the non-expansive set. Then if you take a vector in this non-expansive set, then it means you have another geodesic joining the 2 points at infinity. And that means that somehow stable and unstable coincide. So you have some kind of, can rephrase that in terms of Jacobi fields. They coincide, and therefore the Lyapunov exponents of this measure must vanish. And since mu was an arbitrary measure, you get that the metric entropy is 0, and therefore the topological entropy is 0 as well. So in other words, in dimension 2, all the conditions which are made so far are all satisfied. So that's an important statement. However, you have to be aware of the fact that this in higher dimension not true. So in higher dimensions, already in non-positive curvature, there are situations where the non-expansive set can contribute to the entropy. You have this entropy gap, but it's not like that the topological entropy of the non-expansive set is always 0. And I don't have time to talk about that, but there's a nice three-dimensional example of Gromov. Of course, he was not intended on study this from a dynamical point of view, more from a geometric point of view. And looking at this example, you see that the topological entropy of the non-expansive set can be strictly bigger than 0. Okay, so if you ask me a question, I can produce this example, but I don't want to use the time now to explain this because it's also older work, and you find it also in my old article. And now the question, so now the idea is somehow maybe the 3 conditions are enough to get the uniqueness of the measure of maximal entropy. And I have here a remark that it might be possible to prove, I didn't try that completely, uniqueness under the assumption of H1, H2, H3 as in my old paper, but there are some difficulties. One difficulty is that you lose complete convexity, so Hall spheres are not convex, you don't have this flat strip theorem, and all of this is not satisfied, and therefore if you I mean, it's probably possible, but we didn't do that. One reason is also that there's a certain co-author, one of the co-authors, Klimenhager, and Thompson, they somehow developed a theory which is suitable to apply here in our situation, and I will explain what that is and how we use it to get the uniqueness. So, and of course, this work of Grimmenhager and Thomson is it's also of importance beyond geodesic flows, and it's also closer to the approach of Bowen when he proved uniqueness. Because
excuse me,
yes,
Gerhard, I have a question. In your paper, you made 4 hypotheses. What about the hypothesis?
I come to that. I come to that. This is I could give this hypothesis right away, but that's maybe it's not from a direct from a point of presentation, maybe not very wise. So the fourth condition comes up during my talk. But now I think we could, and actually to be, I believe it's not necessary. It's just a technical thing. I think the fourth condition is a technical thing, but the way we prove things, we need this condition. So I come to that. Okay. But I'm more interested in the 3 conditions which we made, and I think they are sufficient, but we're not quite. And especially if I would be able to prove it in the way I did it in this 98 paper from 98, then I would not need it. And another way is, I talked about that to Bochum Grimmenhager, he would have to rewrite his paper with Thomson a little bit, and maybe then it would be possible to get around this fourth condition, which I did not mention yet. Okay, so let me recall. So I just want to recall what their work somehow was and what the results are. So it's called, the point is about expensivity, coarse specification, and then at the end, a unique MME. And actually, this works completely in a non-differentiable setting. I mean, you just have continuous flows. And this was already somehow a version of that was in the 70s produced by Franco. So I didn't know about this paper, but they had something like that. But this is much more general what Grimmenhager and Thomson is doing. And you need 2 definitions. One definition is expensiveness on scales, which depend on scale. And the other is this coarse specification, which then also depends on a chosen scale. So the first definition is quite easy. You start with a continuous flow on a compact metric space, and you call an orbit expensive, orbit FTX expensive at a scale epsilon, if essentially you look at orbits which stay epsilon close to this given orbit, and there should be essentially only one orbit. So then it should somehow coincide with the other orbit. So that's what this condition means. So gamma epsilon x is a neighborhood of orbits which stay epsilon close, and they should be included in the should somehow be all on the same orbit. That's what it basically means, and that is called expensiveness on scale epsilon. Epsilon can be quite small, and then if you fix epsilon, you have this set of all orbits which are expensive at the scale epsilon, and then you define, as I did before, as a complement, which is non-expensive at scale epsilon. And now the idea is now similar than before. So you look at the topological entropy, which depends now on the scale epsilon, on all measures, or you take the supreme over all metric entropies which are supported, where the measures, the invariant measures are supported on this non-expensive set. Okay, and that you call the topological entropy of this non-expensive set. And now, similarly as my condition before, we have you say that the flow has an entropy gap at scale epsilon if this topological entropy is smaller than the topological entropy of the complete flow of everything. Okay, so that's just one definition. And the other definition is more from a dynamical nature. So it's about specification. So specification has been introduced by Bowen, and here it's a kind of a generalized type of specification which depends on a certain scale. So what does specification mean? It means basically it's a kind of a shadowing thing, only that's a quantified shadowing lemma, so to speak. So that means if you take any finite collection of orbits, so you take points and orbits running from 0 to ti from some time, and then you want to approximate that by one orbit. So that's the usual thing what you do in shadowing. And so according to this given finite number of orbit pieces, you want to find an orbit which so there are capital T1, T2, Tn, and they correspond to the times the orbit gets close to the orbit pieces. So the orbit should approximate this orbit pieces. So that is written here. For instance, if you take, maybe it's easier to see the picture, you have one orbit piece from x1 to ft1 x1, and the time capital T1, you look at the orbit at ft1 of epsilon at time ft1, and then you follow up to the same time the orbit piece, and then the orbit does something, and then it will approach it again, and so on. So it's kind of this kind, that's what this estimate tells you. And the approximation should be done up to the scale delta, so there should be delta close. And then, of course, that would be always true if you have a transitive or dynamical system. But here it's important that the transition time, the time which you need from one approximation to the other, should be bounded. So that is the second condition. And it should be universally bounded. So there's this tau, and this tau is a priori given. It does not depend on the orbit, on the number of orbits, and not of what kind of orbits you take. The transition time is always finite and bounded by this number tau. So that what's called specification at a scale delta. So you have now two things: expensiveness and on a scale, and specification at a scale. And those two things are now coming together in a result. So first of all, if you have an Another flow, then you are always transitive Another flow, then you always, as well known, we have the specification for each scale, but in general that might be not true. And this is therefore a more general setting. And now comes the theorem of Klimmenhager and Thomson. And again, the assumption is as before, you have a continuous flow on a compact metric space. And now you assume that you have an entropy gap at scale epsilon. And if you have a specification at the same time as specification at scale delta, and if epsilon is bigger, so of course if epsilon is bigger, it's more difficult to get this expensiveness. So if epsilon is bigger than 40 delta, then whatever 40, I'm not sure why 40, but it's probably not optimal, but there's some number, then FT has a unique MME. So it has a unique measure of maximal entropy. You see, if delta is now it's a bit tricky with this condition, because if delta is very large, then if epsilon is bigger than the diameter of your compact metric space, then that cannot be true, because then you cannot have expensiveness. So that means if you are punished, if the delta is large, you might not get this required estimate. You see that this is a kind of a tricky condition. So somehow to check that this that you have a situation like that. But that's somehow at least a criterion which would then imply the uniqueness of the MME. Okay, so I cannot say too much about the proof. It's basically inspired, of course, by a Bowen. It's a Bowen type proof. So if you know the proof of the uniqueness of the MME by Bowen, and then also for metric spaces by Franco, then you simply try to follow their argument, and then they get it at the end. Okay, so that's exactly that I use as a black box at the moment. So I am assuming that we have this and we want to apply it to our situation. So, okay, how do we apply this to our situation? So I have here a lemma. And the first lemma somehow guarantees that you have an entropy gap at scale epsilon. So remember that in my definition, which I gave, there were no scale, there were only expensive set, and this expensive set somehow, there was no scale involved at all. Huh? So here I have to now to deal with this scale. And the first lemma tells you that you have an entropy gap at a certain scale if you have the following condition. So, okay. That means we start with the remaining as before, with a manifold without conjugate points, which have these three hyperbolicity conditions, H1, H2, and on top of that, this condition H3, which was something about the entropy of this expensive Z. It's not related to scales. I have to do this relation later. And the claim is, and we'll see that's not so difficult, that under this assumption, the geodesic flow has also an entropy gap at scale epsilon, provided epsilon is smaller than the injectivity radius with respect to this metric. So you want that, of course, if epsilon is too large, you cannot have expensiveness, so that's clear. And but the assertion is that if epsilon is smaller than the injectivity radius, then everything is fine. And the metric, so as we used it already last time, a natural metric to use is the one given by geodesics. So you define the metric of the distance of two vectors just by being the maximal distance of geodesics starting at V and W, where you take the maximum or a time window of length 1. Okay, so that's my metric which I use. And now I want to prove this result. And so we have to show that yeah, I will go ahead with this. So we take now a non-expensive vector at scale epsilon. And epsilon is assumed to be smaller than the injectivity radius. So that means that there exists a second vector. If it's not expensive, then there must be a second orbit. And the second orbit will stay by definition epsilon close to the given orbit in where we start off with. So this vector V. So there is by definition a second orbit such that the distance is smaller than epsilon for all time. And now comes some important fact about the injectivity radius. The injectivity radius, this assumption guarantees that we can lift. You remember that the expensiveness was somehow defined in the universal cover. So we have to check something for lifts. So that there exist lifts of the two geodesics with initial condition V and W, which also on the universal cover stay epsilon close. So that's important fact. If you would not have that epsilon smaller than the injectivity radius, there's no way to deduce this, so cannot diff them to stay close to for epsilon close for all time. That now means that our two geodesics, or better to say that our vector V corresponds to a vector in the non-expansive set. Because these two geodesics which you create here, they have the same point in infinity. Because they stay epsilon close, and by the definition of the topology at infinity, they are the points at infinity are the same. So, in other words, this vector V in the non-expansive set of scale epsilon is also non-expansive in the sense which I introduced at the beginning. So it's a vector which corresponds to a geodesic which does not uniquely join 2 points at infinity. And then it means that if you have now an invariant measure which has full support on the non-expansive set up to scale epsilon, since non-expansive set at scale epsilon is also a subset of the non-expansive set in the sense which I introduced at the beginning. You have that this also has a full measure, and therefore the metric entropy of this measure is smaller than the topological entropy of this non-expansive set, but that has now a gap. It's smaller than topological entropy, and therefore is the assumption. So you have that this entropy gap in the sense of Alemanha and Thomson is fulfilled. So the entropy of this is smaller than the topological entropy. So that means this assumption is fulfilled, and but here important is that the epsilon is smaller than the injectivity radius. Did you get it? Because it's a bit kind of a stretch. You have to use the notion of expensiveness as expensiveness of a certain scale, which we need by from Alemanha and Thomson, and the expensiveness in the sense by looking at geodesics on the universal cover. And this is a relation of this now. Not complicated, it's maybe a bit somehow confusing, but it's certainly not complicated. Okay, that's what we get. So in other words, let's recall the statement: if epsilon is smaller than the injectivity radius, then you have this entropy gap. Did I write it down? Oh, okay. And now the second lemma is about specification. And this uses very much the existence of the second metric of negative curvature. Now let's assume again this standing condition H1, H2, H3. Maybe I for this point I don't need H3. I only need H1 and H2. Then the assertion is that there exists delta, which depends only on the two metrics G0 and G, such that the geodesic flow of our metric G has a specification at scale delta. And moreover, now comes this problem, this assumption in particular, if the injectivity radius is bigger than 40 deltas, then Phi has a unique MME. And then, of course, if delta is too large, it will never be smaller than the injectivity radius, because you don't have any control on the constant delta. The delta constant might be quite large. That's a problem with this thing. And then we will see later on how we need an extra condition to make that applicable to our situation. Okay, now a sketch of the proof. Can make a complicated proof, but in principle it's easy what happens. We know that, of course, the geodesic flow of this metric of negative curvature has specification at any scale. So we can fix the scale or 1/2 or whatsoever, it's not important. So we have that your metric G0, better to say the geodesic flow has a specification. And then you use Morse shattering. So you know that the orbits of this metric G stays up to a certain constant close to the orbits of the metric G0. And then this is might be a large constant. It's up to you. I don't have control on this, but in principle, I can write it down. So you get a specification of a certain constant delta, which depends on the constants in the Morse shattering. So Morse shattering was just that I can somehow relate orbits of this negatively curved metric to the orbits of this metric G, but the constants, the approximation might be not very good. And now, why do we get a unique MME? We get a unique MME if we can, if 40 delta is smaller than the injectivity radius, because if this is the case, I can pick any number between 40 delta and the injectivity radius. And I said in the lemma before, if the epsilon is smaller than the injectivity radius, I get the entropy gap. So in other words, applying lemma 1, we get that Phi has an entropy gap at scale epsilon, and then finally we use Glimenhager and Thomson, and this implies then the uniqueness of the MME. So this only works, or can only work if we do something with this injectivity radius. The injectivity radius is kind of given by the manifold, and there the force condition comes in. So, so we cannot go, if you want to use the theory of Glimenhager and Thomson, we have to do something. And this is now a topological, basically a topological assumption on the manifold, which is again fulfilled for surfaces, or maybe also for three-dimensional manifold. But in general, it's not known. So so it's a condition on the fundamental group of the manifold. So this is probably quite known in group theory and geometric group theory or whatsoever. You call a group residually finite if the intersection of subgroups of finite index, if you intersect them all, then the intersection will be trivial, will only correspond to the identity element. So you get larger and larger subgroups, and at the end you have that this intersection of all this is smaller and smaller. So it's this way. Sorry, smaller and smaller subgroups. At the end, the intersection of all this, which all have finite index. So in the torus, it's more less clear how to do that. But in more complicated fundamental groups, this is really not a non-trivial thing to check whether this is true or not. And how do we use this? So we assume that will now be our force condition. We assume that our fundamental group has this property. And why is it useful? Because if you have this topological property, then we can go to finite covers. We can introduce finite covers which have arbitrarily large injectivity radius. So assume now that we have a smooth manifold without conjugate points. It's maybe not important, but it's important that they have a large universal cover. So this is guaranteed by no conjugate points. and assume that the fundamental group is residually finite, then for any fixed number R, whatever you take as a number, you find a Riemannian manifold, which is a finite one cover of your given manifold M, which has injectivity radius which is bigger than this a priori given this number R. So you can make injectivity radius arbitrarily large, and so this Riemannian cover is then, of course, locally in isometry, and it deduces a semi-conjugacy between the geodesic flows on the manifold N and on the manifold M. So that's an important dynamical fact, that the two flows are related by this semi-conjugacy. Okay, now I'm more or less done with what we need. And I can state this result shortly with Knieper and Var. And as I said, the fourth condition comes now into the game. So we now assume that we have a Riemannian manifold without conjugate points, such that the fundamental group is residually finite. And on top of that, there's dynamical hyperbolicity conditions H1, H2, H3, entropy gap, existence of a metric of negative curvature, and this other thing about divergence of geodesics is fulfilled. Then the claim is a geodesic flow has a unique MME, and since we already have one, it's the one induced by the Petersen-Sullivan construction, it will be the measure of maximal entropy induced by the Petersen-Sullivan construction. And in particular, the measure has full support. That would not be clear if we just would use Knieper and Thomson. They don't say anything about the support of this measure, but because we know this from the Petersen-Sullivan construction, it has full support. And since it's unique, it's ergodic, and then comes on top of that, which is a result which I mentioned last time already, using techniques from Babylon. Once it's ergodic, you get also that mixing. So it's which is important not for this result, but it's important for other applications. So it's in a mixing measure, and I think nowadays it's known as Bernoulli. Yeah, it's good. Okay. Okay, now the proof is now more or less clear. So you assume you have now that your manifold by assumption is has a residually finite fundamental group, and then we choose a finite cover such that this injectivity radius is bigger than 4D delta, where delta is this constant which only depends on the two metrics, G0 and G. And then, of course, if you have this finite cover, the finite cover will have the same property then, at least the properties H1 and H2 and H3, which we needed, are all satisfied also for this finite cover. Because locally the finite cover looks like the manifold M itself, and H2 is actually only a condition on the universal cover. Of course, N has the same universal cover than the manifold M, and therefore these three conditions are fulfilled, and therefore the geodesic flow on this cover has a unique MME. But now you use the fact that this flow is semi-conjugate to the flow on the manifold M, and therefore you deduce also that, so we have to work a little bit, but that then also on the manifold M, the geodesic flow has a unique MME, since the flow is semi-conjugate to the geodesic flow on N. So that somehow is then the end of the proof, but as I mentioned, I don't believe that one really needs this residually finiteness. Well, of course, a proof needs it, but I think I mean, in my work, I never used it before. And as I said, if we could prove it directly, this uniqueness without somehow using Klimenhager and Thomson, then of course residually finite would not play a role at all. So of course, a nice thing at least that that's true in dimension 2. So for surfaces, there's no condition at all. For surfaces, all conditions are fulfilled, and that means in particular that if you have a geodesic flow without conjugate points on a surface of genus at least 2, then it has a unique MME. So that's a clear statement and does not rely on any conditions, further conditions. But as I said, I think the residually finiteness should be removed, but and that probably can be done. I'm pretty sure that can be done. Okay, the other condition, H3, with this entropy gap, something like that you need. Of course, it's clear that if the entropy of this non-expensive set would be the same than of the full flow, then of course that cannot be true. But I have no example where this actually happens. That the non-expensive set has the same entropy than the entropy of the complete flow. Okay, then that's what this in this paper, which appeared this year in Advances, we showed. And then so I have 2 minutes. Of course, cannot say much in 2 minutes only. I mentioned another result or an application. Of course, these measures are not, of course, it's nice to have a unique MME, but you want to do something with that. It should have some interesting consequences. And already in Margulis, he used this measure to do something with it. And Margulis came to this very nice, precise estimate on the growth rate of closed geodesics. And we can basically get the same result in our setting, what Margulis did in negative curvature. And the final statement is the following. So we assume we have this closed remaining manifold and this first condition, which is residually finiteness of the fundamental group. And then, yeah, okay, I formulated like that. If the conditions, hyperbolicity conditions H1, 2, H3 are satisfied, then the following is true. So what do you actually count? You do not count closed geodesics. That by itself would not make sense because there might be a continuum of closed geodesics which are staying in a small strip, so to speak, and therefore it's better to not to count closed geodesics, but to count free homotopy classes. So you identify geodesics in the same homotopy class. And if I denote by Fm the set of free homotopy classes, I can look at the following growth functions. So you look at all homotopy classes which have the property that they contain a closed geodesic. In negative curvature, this is unique, but in our case, it's not unique. Closed geodesic, such that the period is smaller than t. So you look at all this homotopy classes, and then you take the number of this. And the assertion is that under the condition, which I stated above, you get the following asymptotics. So the number grows like e to the ht divided by ht. It's usually called Margulis estimate, because what Margulis proved in negative curvature, or better to say for certain Anosov flows. And this means that the ratio of the two terms on the left and right hand side converges to 1 as t tends to infinity. And that I find really, I'm still very much amazed about this result of Margulis, I would say, because I remember as a student, I was in Bonn, and in Bonn there were not so many people in dynamics, and of course, Anosovs once in a while were visiting Bonn, but in Bonn itself, there was Klingenberg, and he didn't know too much. He knew something about dynamics. But this result, I thought there must be a mistake in Margulies' proof. I didn't believe this because there was only the 3 pages proof which appeared in the West, and we could not get exit how he did it. And but it's amazingly that this is true. If you remember that you have a very much flexibility from a geometric point of view, you can vary the metric whatsoever, and you get this precise asymptotics, which before Margulies it was only known to hold in constant negative curvature, where you use the center trace for techniques to get this result, but beyond non-constant curvature, this is a really amazing result, I would say. And now, of course, we are building on results on ideas. So how do we prove this? The proof somehow uses very much the ideas of Margulies. Only that the same proof does not work because Margulies somehow introduced these flow boxes, which are generated by stable and unstable manifolds. Since we don't have really transversality, we have to make this local product structure, which somehow is used. And he used this, and we replaced it by looking more on a replacement using the boundary structure. So that's the way this proof is working. And I also should mention that recently there's another paper by Rix. He somehow proved this theorem. I think it will be published soon, but in my case, so which I studied before, non-positively curved manifold. So if you have a non-positively curved manifold of rank 1, then this result is also true. When I proved it, I got a weaker, I got not the same asymptotics, I got it only up to some multiplicative estimate. So you have some constant involved, and I could not get this precise estimate. And this precise estimate is differently. I'm pretty sure that without using mixing and all the things, you cannot get this. So it's impossible. So, yeah, mixing is a very important tool. So I somehow intended also to say a little bit more about this, but of course, with lack of time, underestimated the time needed to explain things. So cannot go beyond that, what I just as a statement somehow. Of course, there are many more open problems. So here we always have this conditional conjugate points. Of course, you would like to remove this, and then that's where you have to do something else. And I was thinking of looking at a subflow, which is not a complete geodesic flow, but if you have such a surface of higher genus, you have a subset of geodesics, which are the so-called minimal geodesics, which were already introduced by Coarse and so on. And you look at the dynamics of this subset, and I think this subset then also has a unique measure of maximal entropy. And that would be somehow also what one could try to prove. And but that's a lot of things which you might be able to do later on. Okay, thank you very much. So thanks for listening, and hopefully you got something out of the talks. Yeah, okay, thank you very much.
Thank you very much. Are there any questions or comments? I think Catherine already.
Yes, I have 2 questions. Thanks a lot for the last part of your lecture. Was very inspiring. If you, in the beginning of your course, you pointed out the relation between entropy and the volume growth. So
yes,
if you change this function P of T, you just explained, to the volume growth, fix a point and study the volume.
Okay. Yeah, that's another question. So if you want to look at precise estimate on the volume growth, I think it's possible. So I think though that's also what actually also Margulis did in negative curvature. So if you want to, so I should say, if you depends what you want, with spheres or balls, it doesn't matter. Say you take a ball or a sphere, doesn't matter, of radius r in the universal cover. So it's a ball of radius r. Then I guess one can also prove that this ratio would converge, and it will converge to something, and even a negative curvature, of course, known by Margulis, to a function a of p. And it turns out, at least the negative curvature, I know that, so you remember the Margulis, the Petersen-Salve measure. The Petersen-Salve measure were finite measures, but certainly not probability measures. So the total mass of the Petersen-Salve measure depends on the point P, and this function a of P is exactly, so I guess the total is the total mass of the Petersen-Salve measure. So that should be Petersen UP of the boundary.
Okay. What's the variation when you vary P?
Yeah, that's a question. What is regularity of this? And I think a negative curvature is even it's a smooth function, and I think there should be some rigidity involved to that. That this function is never constant unless you are in a homogeneous case. That has, at least I think this is you did something on this, and student of Katok, negative curvature, and I think in dimension 2 it's clear, it's more basically clear that this A is only constant if the metric has constant curvature. It's related to something else, what I also did. It's about spherical averages. So if you start with an average function over geodesic spheres, you can look at these measures, which they will also define a measure, and then you can ask yourself whether this converges to the Liouville. It's a Liouville measure, or it's another measure, and I proved that the spherical average never will converge in dimension 2. It only converges to the Liouville measure if you are in constant curvature, and this is related to this, to spherical averages.
Okay.
So so this is a negative curvature is quite well known, but in this setting, it's probably also true, but it's not written down somehow.
Okay, thank you. And I have a second question. In your proof, you showed that you have this specification property on a given scale, which is related.
Yeah.
But don't you need for this Klimmenhauer-Thompson proof that you have specification at any scale? But the
no, that's the whole point. That would be useless. I mean, Klimmenhauer, they only needed some relation between the expensiveness thing and the specification. So you need epsilons being bigger than 40 delta. And as I said, if delta is large, then it's quite likely that it's not expensive on the scale.
No, but you need to go arbitrarily. I mean, the shadowing orbits must be arbitrarily close. I mean, this is usually
no. That's not the case. That's not.
Yeah. For some examples, they use that this holds, and then their conditions. So their conditions are very finitary in the sense that you just need for some fixed parameters.
Yeah.
Okay.
Yeah. But the delta should be not small. Of course, if you want to somehow realize that epsilon, the expensivity should be still true, because epsilon should be bigger than this. That's a problem. And then delta is too large, so you're not getting anything. That's a problem.
Okay, thank you. I will
This
check
is the relation between that is a tricky, it looks quite nice, but then if you want to apply it, and we only could do it by using this trick with this covering things that they make the EGT radius large, and that, but that's a kind of, I think it should be not necessary. It should be, it should get rid
You
of
think
it.
it's an artifact of the proof, right?
Hmm?
You think that this residually finite is an artifact of the proof?
Right. It's, I'm 100% sure about this.
Are there other examples where you have a, let's say, a non-finite cover?
I think it's not much known. I mean, maybe it's true always that you have this. At least, I'm not sure if for any manifolds there should be some counterexample that you have this situation. I'm not a topologist, so I don't know what I use it as a tool, but I think at least in the case of course now we have a metric of negative curvature. You can assume that as a background structure, you can assume that the manifold has a negatively curved metric, and under this assumption, I'm not sure if this is always the case. There are no counterexamples. I don't think so. For whether there are fundamental groups which are not residually finite in this class of manifolds which carry a metric of negative curvature. But that's good. Maybe I think in dimension 3 it's proved. There's also something in 3 dimension, but in higher dimensions I'm not sure. But I think I'm pretty sure that's not the right thing to do. One should get rid of this assumption.
Are there any other questions or comments, Yuri?
So
yes.
Yeah, you can ask Adin first, and then I can go later.
Oh, thank you, Gerhard. Are there other results in the direction of proof the gap entropy in other categories of manifolds?
I think in the Riemannian setting, I mean, this has been used now twice. So the one assumption was one application was a case of non-positive curvature by Burns, Klimlager, and forgot Fischer and somebody else. They got another proof of my theorem, and as I said, a bit more general situation, and now this result. So maybe they probably use it also for billiards. I'm not sure for certain other dynamical systems. But I'm not. I did not follow all applications of the result. Maybe or they try to apply to this, but in a geometric context, that's the only application so far of the result.
Okay, I have a second question. I've lost about what is the more general setting in what you can construct a measure of maximal entropy through the Patterson-Sullivan measures.
I didn't get it. What's the question?
What is the more general setting in which you can construct the measure of maximum entropy?
Where you don't have this assumption where you cannot construct a measure. Okay, I mean, there are two things. I mean, the existence of a measure of maximal entropy, I think it's known in a very general context. Yeah, I think you need something like, it's kind of, you need some weak expensiveness somehow, very local, I mean, in the sense of Newhouse, something like that. You need, maybe it's even true if you have a C infinity flow, yeah? If you have a C infinity flow, you get a measure of maximal entropy. And, but then you don't know much about this measure. So you have no idea what's going on, and they don't have any reasonable representation of this measure. So in principle, I mean, maybe if you put other conditions into the game, then maybe you get more information about this measure, but in general, not. And but uniqueness is a completely different thing. I mean, this is very complicated. I mean, for instance, I didn't mention this, but the uniqueness already also implies that the closed geodesics, which I mentioned here, are uniformly distributed with this measure, because you can, if you have separated closed geodesics, so in this case, which I'm looking here, you are looking at closed geodesics staying in different homotopy classes, they are separated. And using this closed geodesics, you can build up an invariant measure, because the growth rate is equal to the topological entropy. You get another way of representing the measure of maximum entropy by averaging over closed orbits, and that means that the closed orbits are uniformly distributed with respect to this measure. That's also another useful or nice application of that. So you have many different ways of representing this measure, depends on your point of view. Either you use closed geodesics, I mean, Margulis initially had even a different way of getting this by looking directly at stable and unstable manifolds, and he first constructed this measure on the stable, this Margulis measure on the stable manifold, and then he used this to construct at the end an measure on stable and unstable manifold in that way. That's even a different representation of the measure.
Okay.
Many different ways of.
I think you're running out of time. We have a short break for lunch.
Sorry.
Can I ask? So Yuri wanted to ask the last question, or maybe you?
No, sure. I just wanted to make sure that the expensive and the non-expensive sets that you use are the same ones that were used in the non-positive curvature, right?
The construction is the same.
Okay.
Not the proof. The proof is completely different.
Mm-hmm.
Proof,
so and
the proof, I would, of course, I would have liked this to prove this with my method, but already to prove, I could not quite manage to prove that the measure which I constructed of maximal entropy is actually ergodic. You see, the problem is that if you try to prove, how do you prove ergodicity? The main tool for that is the Hopf argument. But since the geodesics do not converge, you cannot do not get that the average of a continuous function along orbits are the same on if you start with initial points on the same stable manifold. So this already is a problem to prove ergodicity of this measure. And if you cannot prove ergodicity, you can forget about uniqueness. So that's a sufficient, that's a necessary starting point to prove at the end uniqueness. And therefore I thought maybe it's don't have to work too hard. Maybe we use this the theory of Limnager and Thomson, and then we can do immediately something. So then we can prove it without going through this measure. But I'm pretty sure that it's still possible to get around this Limnager and Bochum.
Mm-hmm. Just one quick question. So the regularity of the horospheres, they play no role in your proofs, right?
There's some continuity of Boseman functions and things like that. Especially if we come to the second result about the growth rate of periodic orbits, because then so what we know is of course that the expensive set has full measure, clearly, with respect to this measure of maximum entropy has full measure. And then we will pick orbits which are in this expensive set. And around this, we build up a certain kind of counting box. And to do this in a reasonable way, we need somehow some continuity dependence of the horospheres on the point at infinity, something like that. But no other regularity is needed.
Okay, Thank you.
Yeah, you need
So-
something.
So I would like to thank again Gerhard Knieper for the wonderful series of lectures. So thank you very much.
Thank you very much. Thank you. Thank you for listening.
Thank you.